weather balloon. An Air Force spokesman confirms tonight that this was no flying saucer.
Okay, on this video, I'm going to be showing this primary coil. It's going to be the primary, and it's a bifiller coil because it's got two windings. But it's not exactly like the Tesla bifiller coil. Number one is not, you can notice it's cylindrical, not pancake type, a little bit elongated. But the point here, essential here, is that I'm using two start points on this, which are separate at each extreme of the coil. And I can take the core off, so I can, and then I have an empty hole, so I can do different testing and so on. But the point here, it's this one. If you follow the movement, it's going like this, and if I get my clock like this, it's gonna be counterclockwise. Now, if I go on the other side, this is my other starting point, which is going also counterclockwise. So what this differentiates from the bifiller coil is that it generates a more symmetric fields when I pulse them separate. And the point why, because both are originating next to the core, the positive pulse, and they're traveling upwards towards the end of the coil. So both ends of the coil are at the outer layer, at the last layer, the both, which are gonna be the negative. So it's a more uniform bifiller, but also, let me say this, also a regular bifiller from Tesla would work. I just like this because it projects a more symmetrical, volumetric, spatial feel. That's all. And so what I'm going to be doing is alternating the pulses to each of the red wires, and it's going to have a common ground, which are going to be the two ends of the wire. It's not that complicated. It is a little bit to wind it. Why? Because I got two starting point, and they're going counter each other and crossing. I call it cross windings, and so on the upper layer, and so on and so forth until I get to the final layer. And this is basically for the exciting coils, the primary coils that I'm going to use, which I'm going to be using the same rotary switch mechanical there, which is going to be alternating. And again, this is mechanical, and it's only switching 6 elements on each coil. So on each side, symmetric from the same distance. And there's 2 empty above and 2 below elements that are not being used. So it is impossible, because the brush takes only 2 elements, it's impossible that it'll be in contact with the 2 coils at the same time. I don't want that. So, but now I have jumper wires on this model, so I can modify the wave to the way I want it. And so far, this is the best setup I have. I got 2 elements, separation above and below. And what I have done here, I got the 2 extremes right here, and I'm going to add the core, and I'm going to start pulsating it, and I'm going to get the cam this way so you guys could see the monitor, the CRT flat line screen that you're familiar with my first video on it. And I want you to see, and I'm just going to start pulsing this positive here. So when I pulse this one, I'm going to create a north pole here and a south pole here. North here, south here. So the projection on the screen is going to be an upper sine, like you saw on the CRT video, and a lower on the right lower quadrant. Left upper, I'm going to have a positive. And of course, it's going to be pulsating. So it's going to be on and off. And I'm going to use this terminal right here. I'm going to connect it right here with these clamps that I have installed to it. And I'm going to at the ground from the source. I'm gonna give some speed to the rotary switch first. I'm gonna go very low first. And I'm gonna start adding and I got 2 meters connected there. I'm gonna zoom over there. And I'm only using like 7.5 volts and like 1 amp. Like 1 amp. So it's a pulsating amp. I think it got disconnected. Yeah. It's pulsating in between. I'm gonna go a little higher so it stabilizes. Yeah. Once that commutator starts running, it stabilizes the input. So I got 9 volts and about 1 amp pulsing. So, but, you know, again, let's remember I have only one coil, one circuit open. And we can see here on the monitor, on the screen, that it is projecting a north pole right there. Okay, and it's on, and then it returns to the flat line once that the field fades out. Because we gotta remember, they don't collapse suddenly, they collapse even, slowly, they come down. And you can see there the sign, the upper quadrant, left upper, positive, and lower right, negative. But now what happens is when I add the other coil, I have to, when I add the other circuit, what you see there is a completely different signal. And of course, it went down in magnitude, the deflection angle, because both are working now with the same input. But you can see that right now we got a south and a north pulsing, and it looks they're taking place at the same time, but they are not. Remember, it is a rotary mechanical switch that only allows one field at a time. So that's what we get. We get the 2 projections here in the same screen at the same time, and that's the speed of this small CRT that can afford, because of the speed of the beam and the rastering frequency, which is about 15 kilohertz. It can scan line the field movement, deflection, spin wave. And the more I accelerate it, you can see the more compact it gets. And you can see there and now after I'm done with this, it's with the CRT, I'm going to take it away, and now I'm going to concentrate on the magnet, on the electromagnet pulsating right here. I'm going to disconnect CRT, and it's out. And I'm going to show with another magnet what the dielectric is doing. I'm just going to get it so I can make it visible, the pulsations right there. See, see right there, you can see it. I have the magnet steady. Of course, I feel in my hand a big time pulsation, and it's not that much current. And in order to prove that, I'm going to lower a little bit the pulsations here, and I'm going to get this rotor from a BLDC, from a brushless DC motor. The rotor has got a north and a south on the other side, and I added a reflective film to be able to scope to measure the RPMs it's going. And if I put it here, you see how it starts rotating. but because of the fluctuation of the fields, it starts going, and you can see that this is a completely spatial field that we're detecting right here, the fluctuations of it. Even from a distance, you can see how it is pulsating. And right at the center, I'm going to have a more steady and better, stronger force, magnetic force, because the center is where both fields emanate outwards to space. So when I increase the speed of the mechanical motor remotely over there, just sending the signals through the wires, I can move the spatial field. This massless, weightless, and transparent field, we can see how it's moving it at the same. And this is another interesting thing here. It's that it is moving it around the same distance that I am. Let's lower the cam here so you can see the RPMs is doing 1400, 1446, and if I project it over there to my rotary switch, we see 1400 too. $14.45, and here we have 14.49. So it's exactly the same ratio we are causing remotely over there by pulsing, sending the pulses through a wire and making this field to move, to flash. Actually two fields that are, one is alternated to the other one. And it's interesting, as I accelerate the speed, you can see now that I'm going here. Let me get the cam lower so I can show the RPMs here. Now the motor is going, the rotary switch is going 2394, and here going 2397. $2,400. Now we're there again. 2,400. The motor, you felt it went a little bit off. 2398. $23.96. So important thing here, we have achieved remotely. We are sending a signal to a stationary coil and ferromagnetic heavy piece of steel core, and we are moving the field back and forth exactly the same as a stator of a rotor field, exciting field of a generator. Identical. We're getting flashes projecting outwards from the center of the core, outwards, north, south, south, north, and so on. So I can set this motor right here, and it'll keep running. And you see the distance it is. This is the influence that the field is doing to this motor, to this rotor. It's rotating even further away. Well, now of course it went out, but no, now it's catch it by spinning it, and we can see how far we can come out around here. And I'm going to start decelerating the motor, and you can see how it goes down in speed. And of course, in the center is more even the movements. Okay, now the test that I'm gonna be doing here is very simple. So I'm gonna add this coil. This it's, as you can see, it's very thin coil, but it's 14 gauge, but much less turns than this, and much less layers. It's got like 4 layers of wire, and the last layer, you can see how spaced apart it is. But what I want to prove here is a simple concept of doing this. Just gonna get it, slide it in, yeah, and align the core. Just gonna touch, solder the 2 ground ones, and I'm gonna keep pulsing the inner primary one with the same, in the same fashion that you saw previously, moving the little rotor magnet. And I have 2 meters back there in the back. That one right there is the voltage of the source, and the right side at the end is gonna be showing the amperage. Now this one here is amperage, is set up for amperage, and it's got these 2 little clamps here. And this one right here is gonna be the output voltage that this outer coil is gonna be sending out. And this one will be reading with these 2 terminals. I'm gonna be reading the amperage here. But simple test. It's gonna hook. Oh, it just came loose again. Let me retouch it. Yeah. Okay, and now I'm gonna pulse both at the same time, both positives. And I'm gonna add these 2 clamps here to show, to connect them with this voltage meter. Okay, I'm gonna get the cap further out so we can have a better view of the whole thing here. Even though I'm gonna start zooming on each setup right here, and I'm gonna start turning the switch, and I'm gonna add power to it. And okay, so the voltage at the source, it's right now at 4.6 volts and like 1 amp. And so now let's look at this. This one is showing it jumps to DC automatically. It's doing that because of the pulses here. It's 1.1 volts. Now I'm just gonna jump wire this core. I'm gonna short it with the amp meter. I want to be able to capture what happens with the input, and it's not further away. So let me see right here. I'm gonna add 1 right here, and the other one right here. And now I'm showing the output on the secondary. And you can see that the amperage below in the bag is about 1 amp still, and here is 1.345. Now I'm going to start accelerating, so all voltage stabilizes. When I get to an operating speed, we can see the voltage went up a little bit, but the amperage is remaining the same, 1 amp, 1.063. But right here we got an output on this very small coil, and watch this, there is a little, it just slide off, but watch when I center it, how it climbs to 3 amps. Because in the center of the coil is where it gets the best of the influence. Okay, so I got 3 amps shorting and of course the voltage went down to 0.353. But the amperage, it rises with the fluctuations of the motor, while the source amperage remains at 1 amp. I got here 3.2 amps, and of course I'm shorting the output. And on the you can see right there on the analog that not too much because of the lamp, but it's remaining at 1 amp. It's 1 amp right there, and the same voltage. 3.2 amps, 1 amp at output, at source input. Now of course the voltage will be amplified the more turns we have here, and the thicker the wire, the higher the amperage, and the more turns and the longer the wire, to compensate we get higher voltage. Still, with this amount of wire that we have in the secondary, I'm gonna get it to and the purpose here is not to demonstrate over unity or nothing like that. I'm just trying to show you that by fluctuating the virtual field, we get power. And here I got this motor here, which is much bigger than that one over there, from a weed eater, an electrical weed eater that I have, and I have it installed to a bridge. What I'm going to do here is install 1 wire to the output of the bridge, and then I'm going to bridge the amp meter to this amp meter, so it records what we're doing here. And the motor of course is connected through the bridge. Now if you notice here, you cannot notice that, but it's pulsating, and we are only getting here 1.5 AC volts. And I'm going to start accelerating, and you're going to see, I want a view of this meter right here. It's important, and also of the back the power source meter. Let me see if I can get a better angle here. Yeah, right there. Yeah, I want to capture both, all meters. I'm going to start increasing speed, and you can see how the shaft of the motor starts slowly spinning and the amperage has increased. That one remains about the same, and actually it's going to come down. Now, all I'm doing right here, I'm not touching the source. All I'm doing right here is increasing the pulsations of the fluctuating two fields back and forth with this very small secondary. And you can see right there, 800 milliamps, and we got at 1 amp. Now watch this. I am going to hold the shaft, and you're gonna see that it only raises like 0.020, and here we got 1.2, 1.3 amps, and I'm holding the motor, but it's got a strength. Its shaft is very strong. It's not going too fast because there's not enough voltage on the system. It's only 3.95 volts, and this is a 50-volt motor. So holding the shaft right here, we go above in amp spent, and this is already wasting the resistance of the diode, the losses of the diode. So we see that the more I increase it, you can see how it keeps increasing to 800 now, while this input remains about the same. Now the voltage because we are pulsing, the coil is feeding back the source. So the voltage, there is a voltage increase in the input when I accelerate. It's automatic. But it's not because I'm dialing nothing on the source. It's just a retro feed, a feedback that is receiving from pulsating this coil. But right here you see we are at 998 milliamps and 778, and it's 1.5. Now there's a relation here, and I don't want to, this is set for AC because it's a pulsating signal. I'm getting it off the bridge, not off the motor, and that is an AC, a DC amperage. There's a difference, but you guys can calculate it. Anyways, I'm going now to disconnect the motor and just disconnect it from the bridge. The motor is going to stop, and I'm just going to short again the output. I'm going to short it with the ammeter, and you see what we have here. We got 1 amp 0.63, and we got 3.4 amps, 3.5 amps at the output with this very small secondary that I got it bigger, and then the results will change. But right now I'm not interested, like I'm saying, in showing any other unit. I just want to show the difference in amperage, not voltage, amperage, between the source and the output, the input and the output. All right, thank you very much for watching, guys. Now, of course, as I decelerate, start coming down, but still there's a huge difference between one and the other. Okay, that's it. I'm disconnecting. Goodbye. I'll see you again.